So I want to make a few general comments echoing what Lenny said this morning, that, and also Juan touched on this too, that part of the message here, part of the message of this conference is, and part of the message of a lot of the progress that's been made in this field in recent years and going forward, is that quantum gravity is not just about gravity anymore. Okay, quantum gravity is really a way of thinking about chaotic many-body systems, and perhaps beyond that, but at least for chaotic many-body systems, it's a way of thinking, a way of getting some intuition that is very useful. Okay, and that's going to be part of the message of my talk, is using some of the intuitions of gravity in order to better understand many-body phenomena. Okay, the goal here, as I think was said this morning, I think Adam said this, the goal here is to realize that there may be systems, chaotic systems, the kind of systems that we're going to be experimentally realizing in the lab very soon, that we can control very well, that are very complicated from an ordinary point of view, but there is another way of talking about them, which is sort of the preferred way of talking about them. The way to actually understand the phenomena is in this other language. So there's an analogy I like, which I say to people every time I talk about this. When talking about the phenomenon of the communication that's happening between me and you right now, right? You don't talk about this phenomenon in terms of the dynamics of 27 factorial molecules in the air. You talk about it in terms of sound waves, right? There's another way of talking about it. That's the preferred way of talking about it. That's the right explanation. And it's more of an emergent type of thing. And quantum gravity is like that for complicated quantum systems. So that's the message. So this paper, but just so we got a little preview of this work from Misha this morning. So this appeared last night, and as a result of discussions between many authors over the past several months. So there are 9 of us here. 9 is a pretty good number. There were also 9 ring wraiths, also called Nazgul. So and you know what they say about too many cooks? Too many cooks make too much food, right? So this paper was a very interesting paper. It started a few days ago at 60 pages, but the published version, we cut it down to 20, but with promises of more details in a follow-up. So stay tuned for even more coming out of this collaboration. I'm not going to talk about a lot of the technical details of the results in this paper. Okay, and in fact, if you ask me about the technical details, I will happily defer to one of my many co-authors, most of whom are here. The thing that I want to talk about is, like I said, the intuitive way of thinking about things, how you can use gravitational intuition and the gravitational picture in order to formulate some interesting questions that you otherwise would not have formulated. Guess the answers to those questions, and then maybe later you can follow up with some more detailed analysis, see that the gravitational intuition was a good intuition. Perhaps, in the end, the gravitational, some kind of literal gravitational picture is not exactly correct, but that's okay. That's fine. You've already won by that point, okay? The victory has happened because you use this gravitational understanding in order to get some interesting results. And this is just what we can do today. Obviously, down the line, by the time we're able to have nice realizations of large n SYK, blah, 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 maybe we can do even more interesting things. But in terms of Juan's meeting in the middle, we can start coming in from both sides one step at a time. Okay, so I'm also not going to spend a lot of time talking about references to, there are a lot of people who have worked on a lot of this stuff. I've collected three particularly relevant references up here whose insights are going to be sprinkled throughout, but I'm there are many other this is a long sequence of work done by the whole community. So this is a guide. We're going to follow this guide. We're going to start, like I always like to start, with a picture that assumes an emergent geometry. Look at that picture. We're just going to we're going to write down some pictures, a few simple equations, a few simple insights, develop some intuition, and then when we're done with that, translate what we've found into some non-geometric formulation, which we can then apply to ordinary simple systems of qubits. We'll discover something interesting, and then we can revisit the geometry. And like I said, sometimes the geometry is gone. But again, you can make a lot of progress rather than looking at complicated equations. As long as you're willing to entertain the emergent geometry picture, you can make a lot of progress just by drawing pictures, writing down one or two actually quite elementary equations, and then go from there. And that's a really, that's a really nice situation to be in. That's also like the Bay Area physics way of doing things. Okay. All right. So here's the picture. This is the picture. All right. I'm gonna consider this conference a success if by the end of this conference one of our experimentalist speakers has this picture in their slides. Okay. Every single theorist has this picture, but I don't think any of the experimentalists have yet. We've gotten close.
We had a similar picture last year, but we could never explain.
Well, yeah. Yeah, so one of the things about this picture is that it's a little scary. Okay, it's kind of a square and some lines, but there's a lot that goes into this picture that you think you have to understand before you can use the picture, but the truth is you don't. Okay, I mean you can use this picture with only a very elementary understanding of what's actually in it. I mean, to use another analogy, you can get the gist of what's going on in Feynman diagrams without knowing anything about Dyson series or whatever. So what are the important parts of this picture? The important parts are there's a left side and a right side. Okay, that's number one. Well, actually, number one is that time goes up and space is left-right. Okay, that's also very important. But there's a left side and a right side. Okay. And things like to travel along diagonal lines. So this picture shows that we've inserted a message on the left side. This middle piece is the emergent geometry. It travels across space through time, and then it hits the top. Okay? The top is the singularity. That means it's not on the left or the right. It just ends up, well, lost for all intents and purposes. And so if you send a message from the left to the right in this picture, or from the right to the left, it doesn't make it across. That's the important thing to understand. But what we want to do is we want to design an experiment where we can send messages from one side to the other. So in this picture, this second version of the picture, there's some extra ingredients, okay? And we'll come back to this picture later on. But the important thing that's happened in this second picture is that the message has made it across. Clearly something happened right here, right, which caused the message to go across. And clearly, by the way I've drawn it, that has something to do with this weird ring here, which I've labeled coupling. Okay, but this is, these are the pictures we want to draw, and then our job is to analyze these pictures, try and extract lessons from these pictures, and then use that to design a more down-to-earth kind of experiment. So that's where we're going. So in order to aid us, we'll go back to the first picture, and a really important insight is to draw an x-axis on this picture, and in fact, an x-axis that goes diagonally. The reason why it's a good idea to draw the x-axis diagonally is because this nicely divides the space into a positive, x positive, and x negative. And you can see that the message that started on the left and didn't make it over just spent its whole life in the x positive region. And likewise, you could imagine things associated with the right, but that don't make it to the left, are in the x negative region. Okay, so far so good. And so you can imagine we can state our goal as saying we want to start with something in the x positive region and have it end up in the x negative region. That's the goal. That's what we want to accomplish. And this is what this external coupling does. Okay, that's what this represents, a coupling that's not part of the emergent space-time. That's why it kind of goes around. Okay, and you can see that what's happening up here, when the effect of this coupling is it causes some kind of translation of the signal from the x positive to the x negative. Okay, and we'll say a little bit more about how we might design a coupling. Okay, so we're going to try and design a coupling that does a translation from x positive to x negative. Now, if all I gave you was pictures, you'd never be able to do it, right? The real secret here is this mysterious thing called the dictionary. Okay, I'm sure everybody's heard about the dictionary. The dictionary is how you translate the pictures, the geometry, the gravity, into something you can do with qubits. There are many entries in the dictionary, it's something that we'll talk about. We'll talk about one or two of the key entries that are relevant for this experiment. Okay, but now we need to talk about some aspects of the dictionary. Only very simple aspects of the dictionary, but that's sort of the trick. One more thing. This message, not only is it at x positive, but it's sort of, you can think of it as being basically localized at some particular x value, right? And it'll be useful in a minute to just recall this elementary fact that, if you think about the wave function describing this message, or say the particle of this message, in momentum space, it would look something like this, okay? Where x naught, some positive number. If x naught were negative, that would correspond to something down here. And in particular, whether this wave function is describing something in the positive x region or the negative x region depends on how the wave function in momentum space winds in the complex plane. Is it going around clockwise or counterclockwise? Okay. Clockwise and counterclockwise is the same as positive x or negative x, and the way we're going to think about it is it's the same as left and right. Okay, this is a thing a nice property that this picture has. Okay, that's sort of the basics of the geometry picture. And now let's talk about qubits. We'll come back to the geometry in a minute. So Misha already showed this diagram. So this diagram, so part of the art here is going from a picture like this to a circuit diagram like this. This involves more aspects of the dictionary, aspects that I won't bother trying to explain. But this kind of circuit, this kind of quantum circuit, again, time is going to go up. This is an ordinary quantum circuit, but normally people don't draw time vertically when they talk about quantum circuits, but time is always vertical for us. This picture here is actually the same as some of those other pictures. Okay, that's another thing that you have to learn is how to translate between those squares with lines into quantum circuits. It's not a complicated language. It's not a complicated part of the dictionary, but I won't try to explain it. The features are kind of readily seen though. This thing that I've called psi in is the message that we're trying to insert. This e to the IGV, this is the coupling, and you can see that there's sort of a left side and a right side. We've labeled these lines, these qubit lines, with L subscripts or R subscripts to denote whether they belong to the left or to the right. Okay, so we insert a message, and then we try to receive the message over here. Okay, and in between, some stuff happens. So I've listed out the procedure on the side here. So on the left, you insert the message, some arbitrary quantum state of a few qubits. The message is scrambled. That's what's going on here. So I haven't told you anything about the dynamics of the system. These Hamiltonians here represent the dynamics of the system. But we should think of it as chaotic dynamics. Okay? Some kind of chaotic dynamics happens. The message gets scrambled. Then we do a very weak coupling between some of the left qubits and some of the right qubits. Okay? Notice, just to make things maybe a little more interesting, we did not choose to couple the qubit that the message was inserted on. Okay, even though so the message was scrambled, but then we left that that particular qubit alone. So it's not like the message just passes through and then jumps over. So the scrambling is actually important. Then there's more scrambling up here, and the statement is that at the end, at least if you trust this gravity picture, at the end, if we've set it up right, if we've appropriately used the dictionary, this psi out should have a very strong resemblance to psi in. In fact, yeah. So the A and the B are useful labels in this diagram. A just means, so A and B together make up the left system, but A is just the label I'm giving to the qubits that the message lives on. So I encode the message not using all of my qubits. The message is just a 1 qubit message, and I stick it in on one particular qubit, and I'm just calling that qubit A, just to give it a name. And then B is all the other qubits. So there are potentially many qubits here, but not necessarily that many, right? You can get away with, I think I'll have a plot later on for 14 qubits total, 7 on the left and 7 on the right, where something interesting happens. So the idea is that if you do something like this, if you do it right, you choose the right coupling, you choose the right dynamics, you should have some, at least that's what the gravity would lead us to believe, all right? But we're not done designing the experiment yet.
HL and HR have to be identical.
There's a relationship between HL and HR. I'm not going to go into details about about the relationship between them. Basically, well, one should be the transpose of the other, but those kinds of details will leave to the paper. This is sort of the thing we need to know about the dynamics. This is the thing that's important about the dynamics from the qubit point of view. So this O, and here's this, transposes appear at various times, but we can ignore the transpose. Think of O as just like a single qubit operator that lives on the left. R is a single qubit operator that lives on the right. And then these are like the Heisenberg versions of these operators.
What is TFD?
TFD? Oh, TFD is this thermal field double state, which makes its appearance all the time also. This effect, or at least some versions of this effect, persist at very high temperatures. So this does not necessarily have to be a low temperature thermal field double state. Just think of it as a state with a lot of entanglement between the left and the right. And this is an ansatz about the dynamics. Okay, this equation does not have to be literally true, but this is the kind of thing that should be true in the systems where this effect is going to take place. And this is something that we label size winding. Okay, what is it? What is going on in this equation? So we've got this Heisenberg picture operator acting on this thermal field double state, and then we expand the resulting state in terms of the Pauli basis. So what is the Pauli basis? The Pauli basis, according to some Pauli string P, okay, P is a Pauli string, it's what you get when you start with like a Bell state and then act with the Pauli string P on one side. You end up with the state P. So you expand in that basis. And the statement is that when you expand this state in that basis, the coefficients, Rp is some real number, the coefficients have a particular phase which depends on the size of the operator P. The size of the operator P, if P is a Pauli string, is just the number of non-identity components of the string. Okay, so it's the size of the operator. And so it's a true fact in certain models that we think are dual to real gravitational systems like SYK, that things like this happen. You get this kind of perfect size winding. But this is sort of a dynamical signature of when you might expect some kind of holographic picture to be accurate. You get a size winding. And the thing to notice here,
On the left side of the equation is a T. Where is the T on the right side?
oh yes, so these coefficients here will depend on T. So when T is equal to 0, for example, there's only going to be one term here. And then when T increases, there are going to be many, many terms. So these RP coefficients will depend on T in particular. So the number of terms will grow with time.
Was the operator O defined on the previous slide?
No, the operator O is just some single Pauli operator acting on, say, on a single qubit, like X, acting on a particular qubit. This is a schematic equation. The important thing about this equation, okay, is that if you look at operators on the left and operators on the right, okay, there's a winding which has a sign difference here, okay, the change in sign. Some of them wind to the left and some of them wind, clockwise versus counterclockwise. Tells the difference between left and right. Okay, this is a thing you can look for in your you pick some dynamics, you ask, does it have this kind of property or some property similar to it? And if the answer is yes, then a holographic picture might be good. That's the statement, okay? And the thing that this should remind you of is it should remind you of this picture that I had before where there was the momentum space wave function, which for x positive and x negative was winding to the left or winding to the right, okay? And so there's a more general pattern here, which is sometimes called the momentum size correspondence, which says that what we think of as momentum in the emergent geometry is the same as operator size in the non-geometric description. Now, I'm being vague and hand-wavy, but that's part of the reason is because the vagueness and the hand-waviness, like you don't need to be terribly precise about some of these things to get it to work. That's number one. Number two is that precise versions of this kind of relationship are still under investigation. Okay, it's not a completely 100% understood thing, but that's okay. It's good enough to get some results. So I'm going to choose to move on, skipping a few more steps. But the statement is that if size and momentum should be identified, okay, and what we want to do is some kind of translation, then the thing we need to do to execute that translation is exponentiate the size. Exponential of momentum is translation, size is momentum, exponential of size is what should be bulk translation. So the coupling we need to pick, this coupling that's supposed to allow transmission of messages from the left to the right, has to be something, this V operator should be something that counts the size of things. It's something that should record the size of polystrings, okay? And you can check that a ZZ coupling does the job, okay? Now, a ZZ coupling is not exactly the same as the sines, but it's good enough because of the commutation relations between x's and y's and z's. And if you're talking about if you've got an operator that's grown for a while, the dynamics are chaotic, you have some distribution over many kinds of strings, then on average, the ZZ coupling will count the size of the operator in a good enough way. It'll be well enough correlated with the size of the operator that this does the trick. The benefit of using a ZZ coupling is that this is you can think of this also as a classical operation rather than using a ZZ coupling. You can measure, so ZZ coupling means there's a Z on the left and the Z on the right. What you can imagine doing instead is measure in the Z basis on the left, and then classically use that information to act with Z on the right, either rotating left or right, depending on the measurement outcome you got. In other words, you can make it look like a traditional teleportation experiment rather than just some kind of quantum coupling. So that's sort of a nice other benefit, which lets you use the word teleportation rather than some other word. And then what about the time evolution? Okay, what kind of time evolution does the job? This, of course, is maybe the real trick. Well, it turns out, now at this point, we've kind of left the gravitational description behind a little, and we're just using this as our intuition to try and find simple systems which may not have literal gravitational duals, but nevertheless exhibit this kind of behavior, okay? And so we can try a few things out. We feel like chaotic dynamics should be important, but other than that, we're just trying some things. And it turns out there's a very simple thing you can do. You can choose the dynamics to be something called, for example, a kicked quantum Ising model. All that means is you have some time evolution operator U, which looks like it has two steps. One is just some Z evolution, and the other is some X evolution. And these things alternate. And with some choices of with some particular choices of B and J, and then these H's should be chosen randomly. And this kind of dynamics will do the trick. So if you take this kind of unitary for the time evolution, you take a ZZ coupling for the V, the coupling V, and you plug it into that quantum circuit that I showed a while ago, then you end up getting some kind of successful teleportation. Okay. In fact, in the limit, at least in the limit where you have a large number of qubits, you can teleport essentially with, you can characterize the channel exactly as some kind of Y rotation plus a depolarization, and you can even get the depolarization to be, to go away and just have a perfect fidelity channel, at least when you have a large number of qubits. But you get something even with a small number of qubits. So for example, here is a plot of what you get when you have 7 qubits on the left and 7 on the right. You use this model, and there's this parameter G that occurs in the coupling. So what's plotted here is the expectation value of Z on the output state when you insert a Z equals +1 eigenstate as the input state. And so there's, more or less, roughly speaking, there's, at least in the interesting parts of the plot, the Z comes out negative because of this rotation effect, and also not all the way down at -1 because of the depolarization effect.
Stefan, what is the scale of the time and the time step?
So one time step is one action of U, and so the scale of that is determined by these coefficients. And I believe for this, the coefficients B and J are both pi/4, and then these H's are like normally distributed with variance 1, I think. Is that right? Variance 1. Variance what? 0.5. 0.5. So that's what a time step is. And you get some, and this is periodic in G. So this is the full. If you continue to larger values of G or negative values of G, you would just see this plot repeat itself. So this is like basically a doable experiment. Okay, it's an experiment that you would not have otherwise thought of if you didn't start with this gravity picture. Once you've thought of it, it's still you can analyze it without the gravity picture, but it's a very interesting thing. Okay.
Did you say what the vertical axis is?
Sorry, the vertical axis. Yeah. So we've got the input state at the beginning, psi in, which is a +Z eigenstate, and then we have the output state, psi out. And then we just measure the expectation value of Z in psi out. And that's the vertical axis here. So if psi in was equal to psi out, the answer would just be +1, right? So you can write down, so the red here is just some simple analytic formula that assumes makes some assumption about chaotic dynamics. And then the black is what you get by doing just a simulation with the actual Hamiltonian or with the actual time step U on the previous slide. And if you take the limit of a large number of qubits, then what happens is you can get all the way down to Z equals -1 for some cases. It comes out negative because there's an effective rotation as well as a depolarization in that case. Okay, but this is a doable experiment. In fact, it's so doable that I imagine that the next time I or someone else gives the talk, we'll be able to show a plot that looks more like this. So I stole this joke from Brian, but this will be very neat. Okay. Okay. So now let's go back to the beginning. Okay. So my claim was that if you accepted some of my statements, is that it wasn't so hard. Okay, if you've never seen it before, maybe it's a little bit of a stretch, but the claim is that it wasn't so hard to go from a picture like this to that experimental proposal, and the answer to what came out of the experiment or the simulated experiment, followed what this diagram suggested it should have been. So now you can just go back and ask, does that quantum kicked Ising model at high temperature have an emergent geometrical description, right? Should this be taken literally? Well, in this case, the answer is no. In fact, there's some other understanding of what this effect is. It's not just some traversal through a semi-classical emergent spacetime. The best geometrical description would instead involve some kind of interference between two different geometries, one that was the original picture without the message, and the other that has a very high energy shockwave in it. And at the end of the day, there's not even really too much explanatory power in thinking of it in that language, okay? But that's okay. Again, by the time we've gotten this far, we've already won, okay? The power in this case was not in the explanatory power of this picture for the final experiment. It was in discovering these experiment in the first place, right? Figuring out what to do. This is I think, a step in the direction toward that middle region that Juan talked about, where we're eventually going to get to situations where it's interesting from all sides, where we'll be able to learn about new things in gravity, say, by studying AMO systems, and vice versa. And this is a step in that direction. That's how I see it. Okay, so what next? I think for the experimenters, this is especially exciting because this is a source of new experimental ideas. Maybe at first, just new, interesting demos of like, oh, this is a fun experiment to do, but maybe we don't learn too much directly from doing it, other than the fact that we can do it. I think an exciting thing to say, at least to say out loud, is that maybe in the coming decade, by pushing this a little further, or perhaps a lot further, we'll be able to do something that qualifies as an experimental test of string theory, which is, again, it's fun to say out loud, even though it would be some emergent string theory. I would say to the holographers, there's more to do on the dictionary. It's the less fuzzy, the better. Lenny mentioned this in one of his questions. Can we figure out some scheme in which we can design experiments that explore the interior of the wormhole? There's some work to do in the theoretical direction for that. Is there some setup where you can imagine, even phenomenologically, some parameters that can be fit that tell you, describe what's the interior of the wormhole depending on how things scatter when they come out? And are there, fewer parameters than there are things to measure? Quantum infolks. This is a thing that I think I just made up for people who do quantum information. Quantum infolks, right? So the emergent geometry point of view, I think it has a lot to offer, even if you don't really fully understand all of the details. And I don't fully understand all of the details, but I know a few entries in the dictionary, and that's enough, to draw some pictures and reach some interesting conclusions. All right, thank you.